we've got ourselves into kind of a strange situation with our work with Taylor series and Maclaurin series. So here's an example of this. So we have this Maclaurin series for e to the x based at, or Taylor series for e to the x based at 0. So it's Maclaurin series. And, we've been saying that this is equal to e to the x. But if you plug in x equals 1, or really any number, what you get here is e to the first, which this is just e, is equal to, right, the sum from k equals 0 to infinity of 1 over k factorial times 1 to the k, and 1 to the k is just 1. But remember that what this is an abbreviation for is a sum where every term looks like this, right, for various values of k. So the k equals 0 term is going to be 1 over 0 factorial, which is 1. And then the k equals 1 term is going to be 1 over 1 factorial, which is also 1. And then the k equals 2 term is, and so on, 2 factorial, and so on. But this and so on right here, there are infinitely many terms here. In other words, this is a sum where we're adding up infinitely many things, right? And that's a little unusual, and that's maybe something that we haven't really thought about in the past. You might remember the Riemann sum idea when we defined an integral back in Calc 2, limit as n goes to infinity of some sum from k equals 1 to n of some stuff. And this might look like it's an infinite sum, but in fact it's not, because, right, even though n is going to infinity, this sum is always finite. And that was actually important for a lot of the properties of integrals we worked out. So that actually isn't an infinite sum. Here we're genuinely trying to add up infinitely many terms. And so this is a new thing. We have to decide what this means, right? This clump of symbols, it has some intuitive meaning, but it doesn't really have precise mathematical meaning yet because we haven't defined exactly what it means. So let's be a little more precise. Okay, let's be a little more precise about what we mean by adding up infinitely many things. So first of all, let's name this phenomenon in general. If we have an infinitely long string of numbers, then adding them all up, so the sum from k equals 1 to infinity of some numbers a sub k, we're going to call this an infinite series, or usually just series. If you say series, most people, I think, will assume you mean infinite series. So we need to give this some meaning. And the way that we'll give this some meaning is just sort of using our intuitive idea of how you would compute such a thing. I mean, how would you compute such a thing? So you'd start with a1, which is some number, and then you'd add a2. Sorry. You'd start with a1, and then you'd add a2 to it, and then you'd take a1 and a2, and you'd add a3 to it, and then you'd take a1 and a2 and a3, and you'd add a4 to it, and you'd keep doing this, and as you went, you would sort of see what happens to the trend as you keep adding more and more terms in order, right? So we're going to need to think about what all of these different finite sums are. So let's name these. This one, it's a sum, so let's call it S1. This one with A1 plus A2, it's a sum, let's call it S2, right? Because we're going out to the second term. And let's call this one S3 and this one S4 and so on. So what we'll do is we'll just think of adding up parts of the series instead of the whole series. Okay, so we'll name these S sub n's. We'll name these the partial sums of the series. So S sub n is the sum from k equals 1 to n of a sub k. And then, so just to make sure we understand what a partial sum is, let's express the partial sums of this series. So this sum from k equals 1 to infinity of k. So S sub 1, right, this series starts at 1. I should say this, but sometimes your series will start at 0. Sometimes they'll start at 1. It kind of depends on context. So whenever you see a series, be sure you look at where it starts. So S sub 1, that's going to be the sum from k equals 1 to 1 of k. So there's only one term in this sum. That's just 1. And then S sub 2 is the sum from k equals 1 to 2 of k. So that's the first two terms. 1 plus 2, that's 3. And so on. The nth sum is going to be 1 plus 2 plus 3 plus and so on down to n, which, if you remember, we've actually seen this one before, sum from k equals 1 to n of k. That was n times n plus 1 over 2. Okay. So that's what a partial sum is. It's just adding up the first several terms in the series. And then to give a value for our series, right, we have this list of partial sums. Well, now we have an infinite list of numbers again, but it's a different infinite list of numbers. This infinite list of numbers we'll call a sequence. So our list of partial sums is the sequence of partial sums. Okay, now that we have these partial sums, well, we want to say whatever these partial sums are heading towards, that ought to be the value for the sequence, right? So if we can figure out what is happening to the partial sums, then we'll say that the value of the series is the limit of the sequence of partial sums. Okay, fair enough, but I mean, before we can do that, what we need to do is think about, well, wait, what does this mean for sequences? So let's talk about sequences, right? We need to understand sequences before we can come back to understanding series. It's kind of an unfortunate collision of terms, or an unfortunate coincidence in English that series and sequence both start with S, because that makes them easy to get confused. So the series is the one that's a sum, and the sequence is the one that's just a list, right? Not only do they both start with S, in a non-mathematical context, a series of things and a sequence of things is almost the same idea, but in a mathematical context, they're very different. The series is the one that you're adding up. I don't have a good trick for remembering which is which. You just have to remember, I'm afraid. Okay, so let's think about sequences. Okay, so a sequence is an infinitely long list of numbers. If we want to write it compactly, we'll use this notation here where, right, if your sequence follows a pattern, you can just put the pattern in these brackets, and then the stuff outside the brackets tells you what values of n are produce terms in your sequence. If it doesn't matter, so always our sequences will go out to infinity. If it doesn't really matter where you start, then sometimes we won't write where you start. Usually it'll be either 0 or 1, but if it doesn't start at 0 or 1, I guess you should explicitly say where it starts. If it matters where it starts, you should explicitly say where it starts. But sometimes it doesn't matter so much. Because sometimes what you're really interested in is just what happens out in the tail of the sequence, in which case the first few terms don't really matter. Okay, right. So another way to express sequences is, right, if you know you're talking about a sequence, sometimes you'll just write a sub n equals, and then the formula for the sequence, whatever the formula happens to be. For example, if we want to write the sequence of evens, we could write a sub n equals, so let's say the evens greater than or equal to 0, right, because there are negative evens as well. So let's see, to get an even number, we have to take some integer and multiply it by 2. That's going to make it even, right? So we could write this. If we cared about exactly where we started, we might want to write 2n like this in our braces, and then be explicit that n is starting at 1. Or if we wanted to include 0 in our sequence, we could write 2n and then say starting at n equals 0 up to infinity, right? For another example, let's look at the sequence of odds. So the odds are just one more than the evens, so we could write 2n plus 1, right? This is guaranteed to be an odd number. I think in this case, you would definitely want to start at n equals 0, so that the first term in this sequence was 1. Right? If you started at n equals 1, the first thing you got from this computation would give you 3, and probably you meant to include 1. Another example of a common sequence is an arithmetic sequence. An arithmetic sequence is a sequence that goes up the same amount each time. So let's write down a sequence that starts at a value b and goes up a each time. Okay, so let's just list the first few values. The first value is going to be b. The second value, well, since this sequence is going to go up a each time, the second value is going to be a plus b, right? Start at b, but then increase by a. And then the next one is going to be, well, take our previous one, which is a plus b, and add a to it again, because it has to go up a each time. But a plus b, that's 2a plus b. Okay, and then the next one, well, we're going to add a to the previous one, so that's going to give us 3a plus b. You can kind of see what's happening if we number the terms in our sequence. If we number them cleverly, something especially nice happens. So if we start at 0, if we call this term our 0th term, so give this the label n equals 0, and this the label n equals 1, and this the label n equals 2, what you can see is happening is that the n value is matching the coefficient on our a. So if we go out to the nth term, we're going to get a times n plus b. And that means the formula for the nth term of an arithmetic sequence is a n plus b. And this one we started at 0. Okay, for some reason I switched the a and the n around, but it doesn't matter which order they're in, right? So an arithmetic sequence is kind of a common sequence. Another common sequence is a geometric sequence. A geometric sequence is a sequence that is multiplied by the same factor each time. So let's say that we start with a this time and multiply by r. The reason that r is the usual name for this is because it's the ratio between terms. Okay, so let's start with n equals 0. Let's label the first term in our sequence with n equals 0 again. So that's going to be b. And then n equals 1, right? We take the previous term and multiply by r. Right? So that's going to give us r times b. Actually, usually people write the r on the other side. And then when n is 2, we take the previous one and multiply by r again. So that's going to be b times r, but that's b times r squared. And then when n is 3, we get the previous one, which is b times r squared, and we multiply it by r again. So that's going to be b times r cubed. But, I mean, you probably see what's happening. If we go down to the nth term, we're going to get b times r to the nth. So why did I switch to b? These should all be a's. I don't know why I switched to b. A is the usual label for the starting term in a geometric sequence. Okay, so in general, a geometric sequence has the form a times r to the n, and the way we've set it up, n is starting at 0 and going to infinity. So there's another sequence. There's one last common way to write a sequence, which is recursive. So for example, here is a sequence. Let's see. A recursive sequence tells you what the next term is in terms of the previous term. So that would look like this. So first, to define a sequence recursively, you have to say what the 0th term is. And let's say a sub 0 is, how about 2? And then you have to say what is the next term in terms of the previous term. So we have to say a sub n plus 1 equals, and then some formula that has a sub n in it somewhere. And possibly even earlier terms. So possibly also a sub n minus 1 and even earlier values. So what if we did something like this? How about 3a sub n? Okay, this defines a sequence because, right, we know what a sub 0 is, it's 2. a sub 1, well, according to this formula, right, if we plug n equals 0 into this formula says that a sub 1, so a sub 0 plus 1, is equal to 3 times a sub 0. But we know a sub 0, it's 2. So this would give us 6. And then we could figure out a sub 2, right? If we use this formula when n is 1, so this was n being 0. If we use this formula when n is 1, we get a sub 2 equals 3 times a sub 1, and we just figured out a sub 1. So it's 6, so 6 times 2, and that's 12. Okay, and we could keep repeating, right? The point of a recursive formula is that once you have figured out the formula out to any position, you can then figure out the next position by using the formula. You might notice that this particular recursive sequence is actually just the geometric sequence 2 times 3 to the n. Maybe the most famous recursively defined sequence is the Fibonacci sequence. I don't remember exactly how many B's and I's and C's there are in Fibonacci, but the Fibonacci sequence, usually it's called F. The 0th term is 1. The first term is also 1. And then the n plus second term is the n plus first term plus the nth term. So I know I said earlier that to have a recursive definition, you have to define the n plus first term. But really, what is important about recursive definitions is that you're defining a later term in terms of earlier terms. Right? That's what's important about the recursive definitions. So let's see. The 0th term is 1. The first term is 1. The second term is the sum of the previous 2 terms. So that's 1 plus 1, that's 2. And then the third term is the sum of these 2 previous terms. So 1 plus 2 is 3. And then the fourth term is the sum of the 2 previous. That's 5. And then so on. 3 plus 5 is 8. 5 plus 8 is 13. And 13 plus 8 is 21. And so on. So that's the Fibonacci sequence, which shows up in some applications that have to do with reproduction. You can Google it if you want.